In this lecture, we can see different types of operations and different types of classifications in the signals. First, we will see representation of signal. Means how can we represent a signal in different number of formats? Representation of signal. So a signal can be represented by using number of ways. One is, first let us take a signal. Okay. One is sequence representation. Sequence representation. And second one is, so one is sequence representation, second one is tabular representation, and third one is functional representation. Yeah, see here. So sequence representation means, let us take as example x of k equals to -1, 2, 3, 1, 4. Here I am placing some mark. Here this mark indicates this is a discrete time signal. Here this mark indicates this is the instant of k equals to 0. K equals to 0. At k equals to 0 instant, the signal of x of k is 3. At k equals to 1, to the right side of this mark, these are the positive instants of time. To the left side of this mark, these are the negative instants of time. At k equals to 0, x of k is 3. At k equals to 1, x of k equals to 4. At k equals to 2, means at second sample, x of k equals to 4. At k equals to -1 instant, x of k equals to 2. At k equals to -2 instant, x of k equals to -1. Okay, so this is the sequence representation of a signal. One more example, 1, -1, 3, 5. If the signal is being given like this, x of k equals to 1, -1, 3, 5, this means if you don't put any mark over here, then defaultly the mark is said to be here. If you don't put any mark in the signal, then defaultly the mark is said to be here. That means this is the k equals to 0 instant. That means this is k equals to 1 instant, 2 instant, 3 instant. That means this is said to be positive sequence. So this is the sequence representation. Means next, tabular representation means if you put same signal, first signal in the tabular representation, that means here we will be having two rows. We will be having two rows, k x of k. K x of k means x axis, y axis. For k, I am putting this signal. I am putting this signal in tabular representation. For k equals to, here we are having -2 instant, -1 instant, 0 instant, 1 instant, and second sample. For k equals to 0 sample, it is 3, x of k is 3. For k equals to -1, x of k is 2. For k equals to -2, x of k is -1. For k equals to 1, x of k is 1. For k equals to 2, x of k is 4. So this is the tabular representation. Next, if we represent the same second signal in tabular representation, see here, k x of k. See here, this is a positive signal. So now for k equals to 0, for k equals to 1, 2, 3. For k equals to 1, for k equals to 2, for k equals to 3. For k equals to 0, x of k is 1. For k equals to 1, x of k is -1. For k equals to 2, x of k is 3. For k equals to 3, x of k is 5. This is how we can represent a given discrete time signal in tabular representation. Next, functional representation means, see here, we will represent the same two signals in functional representation. If we represent the first signal in the functional representation, then see here, x of k equals to 3, its value is 3 for k equals to 0. X of k equals to 2 for k equals to -1 instant, -1 sample. X of k equals to -1, its value is -1 for k equals to -2 sample. X of k equals to 1 for k equals to first sample, x of k equals to 4 for k equals to 2 sample. So this is how we can represent the given signal in functional representation. If we represent this second signal in functional representation, see here, x of k equals to 1 for x equals to 0, x of k equals to minus 1 for x equals to 3, sorry, for x equals to 1, x of k equals to 3 for x, this is not x, sorry, k equals to 2, x of k equals to 5 for k equals to 3. And lastly, we are having one more representation which is nothing but graphical representation of a signal. In case of graphical representation, how we can represent a discrete time signal? See here, graphical representation. See here, here also I am representing the first signal x of k graphically. See here, so this is k and this is x of k. X of k is with respect to k. We are drawing the x of k with respect to k. So this is time axis and this is x of k axis. See here, to the right side of this axis, these are the positive instants of time, these are the negative instants of time. This is k equals to 0. For k equals to 0, we are having the amplitude as 3. This is the amplitude x of k. For k equals to 1, this is having an amplitude of 1. For k equals to 2, this is having an amplitude of 4. Now for k equals to minus 1, this is having an amplitude of for k equals to minus 1, this is having an amplitude of 2. For k equals to minus 2, this is having an amplitude of, for k equals to minus 2, this is having an amplitude of minus 2. In this way we can represent graphically. Similarly, if you represent this signal, see here, with respect to k, x of k, for k equals to 0, it is having 1. For k equals to 2, for k equals to 1, this is having an amplitude of minus 1. For k equals to 2, this is having an amplitude of 3. For k equals to 3, this is having an amplitude of 5. In this way, we can represent a given discrete time signal in sequence representation, tabular representation, functional representation, and finally graphical representation. Thank you. In this lecture, I am going to explain about different types of test signals. These are all called test signals. Test signals means we are having step signal, ramp signal, impulse signal, and exponential signal. For testing the response of any system, we will use these signals. That's why we are calling it as calling them as test signals. First one, step signal. Step signal means, see here. So it is being represented by u of k. Since we are dealing with discrete time signals, we are taking it as u of k. If it is of continuous time signal, we will take it as u of t. So u of t with respect to t is said to be continuous time signal. U of k with respect to k means it is discrete time signal. So it is a discrete time step signal. See here. Here I am taking unit step signal. That's why I am taking the amplitude as 1. For k equals to 0, it is 1. For k equals to 1, it is 1. For k equals to 2, it is 1. For k equals to 3, it is 1, up to so on. So functionally, this is graphical representation. Functionally, if you write step signal, then u of k is said to be 1 for k equals to 0 to infinity. So u of k equals to 1 for k equals to 0 to infinity. Between means between 0 and infinity. So this is said to be as it is having amplitude of 1 for positive values of k for positive instants of time. This is also said to be positive step signal. So if it is unit step signal, then we will take the amplitude as 1. If it is not unit step signal, then we will take the amplitude as some a. A means if it is a voltage signal, voltage step signal, then 10 volts or 30 volts or 40 volts like that. So if it is unit step signal, amplitude will be 1. If it is not unit step signal, then amplitude will be having something value. So this is how we can represent the unit step signal. In the same way, if we take the ramp signal, see here, ramp signal means R of k with respect to k. See here, we are taking discrete time signal. For k equals to 0, it is 0. For k equals to 1, it will be having some amplitude. For k equals to 2, it will be having some amplitude. For k equals to 3, it will be having some amplitude. For k equals to 4, it will be having some amplitude, and so on. So that means if you take the continuous time ramp signal, it will be a straight line passing through origin. But now it is a discrete time signal, we need to take the discrete instants of time. Now this is graphical representation. If you write it in functional representation, R of k is said to be k, ak. So R of k is said to be ak. Ak means, see here, actually in general, in the continuous time signal we will write at, where a indicates the slope. Here I am taking the unit ramp signal. For unit ramp signal, the slope will be 1. Slope will be 1 for unit ramp signal. Slope will be 1 for unit ramp signal. So that means for k equals to 1, it will be having some amplitude. For k equals to 2, it will be having some amplitude. For k equals to 3, it will be having some amplitude. So R of k equals to ak. Now ak means here a equals to 1, since it is of unit ramp signal, and slope will be 1. If the slope is 1, then it is said to be unit ramp signal. If the slope is not equals to 1, it will be some ramp signal. Simply it will be ak. Then for unit impulse signal will be represented by delta of k with respect to k. So impulse signal means it will be having amplitude only at k equals to 0. Here also we are taking the amplitude as 1. So functionally, if you write delta of k equals to 1 only for k equals to 0, and it will be 0 for k not equals to 0. For k not equals to 0, for other than 0, it will be 0. It will be having value only at k equals to 0. Here also, if the amplitude is 1, it is said to be unit impulse signal. If the amplitude is not equals to 1, it is said to be simply impulse signal. Of course, there is a relation between impulse signal and a step signal. See here, if you integrate this impulse signal, then we will get the step signal. See here, if you integrate this impulse signal from k equals to 0 to infinity, then we will be getting signal like this. Then it will be equivalent to step signal. So if you integrate the impulse signal, you will get the step signal. That is a relation between impulse signal and step signal. Means integral of delta of k will be equals to u of k, or alternatively derivative of u of k will be equals to delta of k. Next, exponential signal means here we will be having two variations, exponentially rising and exponentially decaying. Let us take exponentially rising. Let us take x of k. Exponentially rising means this is the variation. See here, means it will be like this, exponentially rising. So x of k equals to e power like ak, exponentially rising, for k equals to 0 to infinity. From 0 to minus infinity, it will be 0. I am taking positively rising exponentially signal. Thank you.